have you gone through the videos of the last week, week 5?
Yes, ma'am.
So based on the previous week content, we'll be solving some questions, and if you have any doubt, you can discuss. So today we'll be solving questions based on Routh-Hurwitz and some performance characteristics based questions. So we'll start with the very basic one. If all roots of a polynomial lie in the left half of the complex plane, then that polynomial is called?
Ma'am, can you please enlarge it? Zoom.
Okay,
Not
sure.
visible.
Now is it visible?
Yeah, visible.
Okay.
Hurwitz polynomial, ma'am.
Yes. So that's a basic definition based question. Any polynomial having all the roots lying in the left half of the complex plane, then such polynomial is called the Hurwitz polynomial. Okay, for this polynomial, find the range of k for which all the roots will lie in the left half of the complex plane. Find out the range of k. This question is based on the previous week concept only. If you remember that, you can solve it very easily.
Ma'am, last option, ma'am.
Last option. Okay, correct. The question is, we are given a polynomial s square plus k minus 5 into s plus 8 minus k. And for this polynomial to be Hurwitz, right, which means all the poles should lie in the left half of complex plane, we know that the necessary and sufficient condition for at least second order polynomial, the necessary and sufficient condition is all the coefficients should be non-zero and there should be no sign change. Okay, so the first condition is k minus 5 should be greater than 0, should not be equal to 0, and 8 minus k should not be equal to 0. Okay, and the second condition is k minus 5 if we have the coefficient of s square is equal to 1. So in order to have no sign change, all the coefficients should be positive because the coefficient of s square is positive. So we have to ensure k minus 5 is greater than 0 and 8 minus k greater than 0. So this will give me k greater than 5 and this will give me k less than 8. Okay, so k should lie between 5 to 8. Last option is correct. For the given polynomial, identify which among these options is correct. The polynomial is s cube plus 4s square plus s plus 6.
Two roots in the right half complex plane and one in the left half.
In the left half plane. Okay, so we will solve this question using the Routh-Hurwitz criteria only. So what it says that we have to form a table starting with the highest degree. So we have s cube, then s square. And how we have to form the table? The coefficient of s cube is 1, and we have to increase in order of 2. So the next will be s. So its coefficient is 1. For s square will be having 4. Another plus 2 degree coefficient is 6. Sorry, minus 2 is 6. In order to find s1, we have to cross multiply it. So it will be 6 minus 4 by 4. Okay, and for another one it will be 0 because there is nothing, and s0 will be, so this will give you 1 by 2. I
Is
think
it
there is
4
some
minus 6, ma'am?
mistake. Yes, yes, yes. That's what I was checking. Thank you. It is 4 minus 6 by 4. So it is minus 1 by 2. And for the last one, it will be
Plus 6.
yes, plus 6. Okay. So there is no sign change here. There is one sign change here, and also there is one sign change here. Okay. So the number of roots in the right half plane equals to the number of sign changes. So we have two sign change, means there are two poles in the RHP, and since the degree is 3, so the other is one pole in the LHP, because there is no sign change and then sign change. So the correct option is option number 3. Similarly, we have the question number 4. Try it first. For this one also very simple. We can write for s cube, s square, s1 and s0. We have 1, 6. Then we have 4, 1. So this will be 24 minus 1 by 4, and then 0, and this will be the same as this, that is 1. So this is a positive number, no need to calculate. Then what we can interpret from here?
All its three
Option
roots in
1.
the left half.
Yes, since there are no sign changes, all poles are on LHP. Now solve for this polynomial.
All roots in left half plane.
All in left half plane.
Yes, ma'am.
Check it carefully. What can I write for S1?
0.
Yes, it is 0.
Zero.
So if I encounter 1 0, then how can I proceed further? Because I cannot write as 0. In that case, it will be the form of 0 by 0 or something by 0. Now how to proceed?
Substitute 0 with a positive number E.
We can put a small number epsilon, a very small number in place of 0. Okay. Now what can we write for S0?
8.
Okay. Okay, yes, actually you were right. This will be 0. So this is all row 0. Sorry. We have encountered a 0 row where we have all the rows 0. Okay. Right. So if we have all rows 0, then what it mean? What we can say about it?
Symmetrical roots.
Symmetrical roots. Yes, symmetrical means there must be a complex root. Is it?
Is it necessary to be complex?
Actually, if you see symmetric roots, so it can be this type of symmetry, okay, or it can be this type of symmetry, or it can be this type of symmetry also. Okay, now why I said complex? Because um, in case of all 0 row, how we proceed further? How can we resolve this all 0 row? We
Take the
have to,
auxiliary polynomial.
yes, we have to go to just above this row and we have to write 4s square plus 8, okay, equals to 0. So this one defines the poles or the roots of this polynomial. So from here s will be equal to, there will be plus minus root 2j, right? So here two poles are lying on the imaginary axis, okay. And what about the other one? So we have to, let's suppose this is ds, we have to find ds, let's write it ps, we have to write d of ps by ds, we have to differentiate it with respect to s, then what we'll get? 8s, right? So instead of 0 we will write 8. Okay, then what will be the last value?
8.
It will be 8 only. Okay, so is there any sign change now? There are no sign change, so we have one pair of pole on the imaginary axis and one pole on the LHP. So which option is correct? Option 1 is not correct because it's saying all three roots in the left half complex plane. Second option is 2 roots on the imaginary axis. This one is correct till now. Third is 2 roots in the right half complex plane. This is not correct. All its 3 roots in the right half complex plane. This is also not correct. So the only correct option is 5. Okay. So any doubt, anyone?
Shows how we could calculate the roots, ma'am, here.
How we?
Calculate the roots, ma'am. There are 3 roots in ma'am.
Yes, there are 3 roots.
We have till
So
now found 2 roots.
yes, 2 roots. So we have actually found out all the 3 roots. One root is in the left half plane and the another 2 are at plus root 2j and minus root 2j. 2 are calculated from all 0 row concept, and the last one we found out from no sign change rule. Okay. Is
Ma'am,
it? Yes.
how can we assume that these conjugate roots will be on the imaginary axis, ma'am? This s
The
is equal to plus minus root 2j is the solution for this 4s square plus 8 equation. It is
yes. So this actually gives you the roots of the polynomial also.
okay.
Yes. Okay, so this is a long question, so I'll read it for you. Consider a second order plant governed by the differential equation is y double dot t minus 9yt equals to ut. It is desired to design a unity negative feedback closed loop control system with this plant. Which one among the following statement is true? So we need to design a unity negative feedback closed loop control system with the plant differential equation given by this. Identify the correct option. First try to find out the plant transfer function and then comment which controller can stabilize the closed loop system. What is PS here? Plant transfer function. It is 1 by s square minus 9. Yes. So we need to find out the type of controller. So we assume that the controller transfer function is some CS. Now if we find out the closed loop transfer function, what it will be? G will be P S into CS, but that is CS by S square minus 9. Then closed loop transfer function is G by 1 plus GH, and we have a negative unity feedback, so H equals to 1. What will be the closed loop transfer function then? Okay, we can write it as CS by S square minus 9 plus CS. And for stability, we have to study the poles of the system. So where will the pole lie? That we can study from the characteristic equation, which is in this case S square 9 plus CS. Now in order to have all the poles on the LHP, how can we ensure that using the function C of S? First we can see that there is a missing coefficient of S. That is, first we need to ensure that all the coefficients of the polynomial are present. Now here if we compare it with a naught s square plus a1s plus a2, so a1 is 0. Now first we have to incorporate this type of thing into the system, which is a kind of differentiator, right? How can we introduce s into the system? Using some kind of differentiator. The first option we can have is to use a derivative controller. Okay, and then we also have to ensure that all the coefficients should have no sign change. Since this s square coefficient is positive, we should ensure all the coefficients are positive, but here we can see that this coefficient is negative. So how can we compensate it? We can compensate it by incorporating a constant such that their sum is greater than 0. So this we can achieve using a proportional controller. Okay, so if CS has the structure of Kp plus Skd, then my characteristic equation will look like S square minus 9 plus Kp plus Skd. Okay, and in this we have to ensure that Kd is greater than 0, and this term should also be greater than 0 to have no sign change. So Kp minus 9 should also be greater than 0. Then Kp should be greater than 9. But here we have to just identify the controller. So the correct option will be, we need a proportional derivative controller, that is the last option. Okay, in this question we need to find out the gains of the controller. We have already calculated it in the previous question only. Kt should be greater than 0 and Kp should be greater than 9. So option A is the correct one. there is some second order closed loop system, and for that we want that its settling time should be less than 4 seconds. Achieve that, what should be the real part of the closed loop poles? For this question, first you should remember how we calculate the settling time of a second order system. Can anyone recall the settling time for the 2% band?
4 by
4
eta
by
omega
zeta
n.
omega n.
Yes, it is 4 by zeta omega n. And the question wants that this should be less than 4 seconds. So what does it mean? It means that zeta omega n should be greater than 1. Okay. And what are the poles of a second order plant if a plant is square plus 2 zeta omega n plus omega n square? If you have a plant like this, what are the poles of the second order system?
Minus eta omega n plus minus root under d discriminant.
Yes. The poles we can write as minus zeta omega n plus minus under root 1 minus zeta square. So there will be omega n here. Okay, now we have to find out what should be this to achieve this, what should be the real part of the closed loop poles? Minus j omega n. For underdamped system we are considering, the real part is minus zeta omega n. Okay.
Yes.
So from here we have achieved zeta omega n should be greater than 1, but the real part is minus zeta omega n. So if we incorporate minus, then it will be minus 1. Okay. So this is the real part, means the real part should be less than minus 1. The last option. Any doubt? Okay, now it is desired to have the maximum peak overshoot should be less than 18%. In that case, damping ratio, that is zeta, should be this is again a formula based question. We know that maximum peak overshoot for people who are preparing for gate. They should be very fast in calculation, because if such question comes, then what matters is in how much time you are solving such type of questions. Again, using the calculator of the system, because then it becomes challenging to use the calculator given in the system to calculate all these things. Okay, maximum peak overshoot is given using e to the power minus pi zeta divided by under root 1 minus zeta square, and we need it to be less than 18%, means we need it to be less than 0.18. Now you have to just find zeta. Take ln both sides and then solve. How much we are getting? This you will get something like then you can square both sides. You can put the value of pi square and you can solve for zeta square, and from there you can find out zeta. Anyone calculated?
Mm, 0.48.
And zeta should be less than or greater than
Greater than.
0.48. That's the correct answer. So zeta should be at least 0.48. Okay, this one is again, I think, very small. In question number 10, consider a second order plant given
Ma'am,
by, yes,
what's the answer for previous question?
for question number 9, the answer is 0.48.
Okay.
We have plant given as this differential equation. It is desired to design a unity negative feedback closed loop control system with this plant using a proportional controller. Here the controller is provided to you. In order to stabilize it, what should be the gain condition? Again the same question but presented in a different way. First we can find out the plant transfer function. It will be 1 by s square plus 2s minus 4, and then since we have a unity negative feedback, so h equals to 1, closed loop transfer function will be nothing but g by 1 plus gh. Now since we have to care about the poles of the system only, so we can solve for 1 plus gh equals to 0, and this will give us, and the controller is a proportional controller, so cs will be kp only. Then we can write g as kp by s square plus 2s minus 4. Then from here we can write it as 1 plus gh equals to 0 means s square plus 2s minus 4 plus kp equals to 0. From here what should be kp?
Kp should be greater than 4.
Greater than 4.
We have to ensure that this coefficient is not 0 and also it should be positive. That means they should be greater than 0, so kp is greater than 4. Option A is the correct answer.
Ma'am,
Yes.
I didn't get how you added the KP into
Okay, the thing is,
G is equal to KP by.
where? Here you are asking.
Yes, ma'am.
Okay, so if you see the closed loop system, here we have the controller, here we have the plant, and here we have the feedback. Okay, and here we have the input RT, and here is the output Y. So G, if we need to find out, it is nothing but the forward path transfer function, which is C into P. Okay, and P in our case is this one and C is KP. Then in order to find G, we just multiplied C with P, because if we have, you will
Why
yes.
KP minus 4 should be greater than 0?
Okay, this part. For second order polynomial, in order to ensure that all the poles are lying on the left half plane, the necessary and sufficient condition is all the coefficients should be non-zero and there should be no sign change. What it means is, if we have, so this is the standard way to represent a second order polynomial. Okay, to have all the poles of this polynomial to lie on the LHP, a0, a1 and a2 should not be equal to 0. This is condition 1, and condition 2 is a0, a1 and a2 all should have same sign. Okay, now here the coefficients, to ensure the coefficient to not be 0, we first have to ensure Kp minus 4 is not 0. Okay, and the second, in order to satisfy second condition, we are seeing that coefficient of s square is 1, coefficient of s is 2, both are positive, right? So the coefficient of s0, that is the constant term, should also be positive, because we don't want any sign change. And how can we ensure that this is positive? These constant term we have written here, and we have to just ensure that this is positive. Now it is clear?
Yes, ma'am.
For the previous problem, find out the ratio of error to reference input. Reference signal means the input. Now let me write PS for you. So PS was 1 by s square plus 2s minus 4, and CS was Kp. Okay, and feedback was 1. We have a negative feedback with unity h. Then find out the ratio of E to R. In the previous session, we have seen that we can write the error E, which is R minus Y, as R by 1 plus GH. Okay, we have seen this in the previous session. Now we have to find E by R, which is nothing but 1 by 1 plus GH. Now can you calculate?
Ma'am, how is E is equal to R minus 1?
If you see the block diagram of a closed loop system,
Second option, ma'am.
second option is correct. If you see the block diagram of a closed loop system with controller C, plant P, feedback H with negative feedback, in this closed loop system, here is the output Y, here we are providing the input R, and this is error. Okay, now E, from here we can write R minus H into Y. Okay,
Yes.
and Y by R for a closed loop system What can we write? We can write it as G by 1 plus GH. Okay. Then Y will be GR by 1 plus GH. So we can put here GR by 1 plus GH. Okay. Here we can take R common and we take it to left side. So we'll be left with Hg by 1 plus GH. So this will give me E by R equals to nothing but 1 by 1 plus GH. That's what I have written here. And please keep in mind that this E by R ratio is only for negative feedback. If there is positive feedback, then we cannot define E as R minus Hy. In that case, for positive feedback, sometimes the question is given like this and we just put this formula and calculate. But be careful in such type of questions. For positive feedback, E will be R plus Hy. Okay, and then you can analyze what can be E by R. Now solve for this one. What will be E by R if PCH is given like this? For our case, G is again P into C, which is Kp divided by S square plus 2s minus 4. Now find out 1 by 1 plus GH. H is 1. 1 by 1 plus G into H is Kp by S square plus 2s minus 4, which is equal to 2s minus 4 S square plus 2s minus 4 plus K. Have I written? Okay. Which option is correct? Option B. It is clear? Now for the previous problem, steady state tracking error when the stable closed loop system is given a unit step reference input. For the previous question, we are providing now a unit step input and we are ensuring that the plant is stable. Then the steady state tracking error will be. Let me write GS for you. It was Kp by S square plus 2s plus Kp minus 4. Sorry. Find out the steady state tracking error with unit step input. RS is 1 by S. Very simple. We have just now calculated E by R. It was this. Sorry. It was nothing but s square plus 2s minus 4, s square plus 2s minus 4 plus kp. Now R is 1 by s and we have to find out steady state tracking error. So we can use the final value theorem. So E as t tends to infinity will be given as, how can we calculate? S into Es limit s tends to 0. Okay, then this E in time domain, it is E. So E as t tends to infinity, since Rs is 1 by s, it will be s square plus 2s minus 4, s square plus 2s minus 4 plus kp. Rs is 1 by s and we have to multiply with s also. Okay, so this will cancel out. Put s tends to 0, what we will get?
Minus 4 divided by minus 3 plus kp.
It will be minus 4 by minus 4 plus kp only. Option is we can multiply it with minus 1 numerator and denominator, then it will be 4 minus kp. The second option is correct. Is it clear? For the previous problem, we desire the closed loop poles to be complex conjugate poles in the left half plane. This would be possible if we select Kp as, for the plant G, which was Kp by s square plus 2s minus 4. We want the closed loop poles, of course, with unity negative feedback, to be complex conjugate and lie in the LHP. How can we ensure that? What should be the range of Kp so that the poles are imaginary, I mean complex, and they lie in the left half plane? The pole should lie somewhere here. First find out the closed loop poles or the closed loop transfer function. Can anyone tell me how can we solve this question? How should we solve it? using Routh-Hurwitz, or which concept can we use?
Routh-Hurwitz and zero row we have to create, I think.
Um, okay.
For Kp greater than 5.
Um, can we also use the concept of underdamped system? Because for underdamped system, we know that the roots lie on the LHP and they are complex. We just now have seen that the roots are given as, for the underdamped system, minus zeta omega n plus minus j omega n under root 1 minus zeta square. So the roots are on the LHP because this is negative and it is also complex. Okay, so for this problem we have to ensure that zeta is lying between 0 to 1. We need to have system follow the characteristic of underdamped system. Now since we are dealing with closed loop system, we need to find out the closed loop transfer function first, which is g by 1 plus gs into hs, which is nothing but kp by s square plus 2s plus kp minus 4. Okay, and the standard second order plant, we write it as s square plus 2 zeta omega n plus omega n square. There can be some constant here also, we don't bother for the numerator. Now from here we have, if we compare this denominator with this one, we have, we have 2 zeta omega n equals to 2. So zeta omega n is 1, and we have to ensure that zeta should be less than 1. So zeta should be less than 1 by omega, sorry, zeta is 1 by omega n. Zeta is 1 by omega n, and we have to ensure zeta is less than 1, which means 1 by omega n should be less than 1. Now what is omega n here? Natural frequency. Here we have omega n square kp minus 4. So omega n square equals to kp minus 4. So omega n is kp minus 4. Or you can square also, that would be no problem. 1 by kp minus 4 is less than 1. Now can you find out kp?
Kp greater than 5.
kp greater than 5. So kp minus 4 should be greater than 1, then kp should be greater than 5. Set to yes. Kp should be greater than 5. Any doubt?
Yes, ma'am.
Yes.
Ma'am, to find this answer, I have used a property of ma'am, quadratic equations. That
Okay.
characteristic equation is quadratic, sir, ma'am.
Mm-hmm.
If its solution is uh, supposed to be in the left half plane,
Mm-hmm.
then the discriminant should be less than 0. I have
Yes,
used
yes,
that.
yes, yes. Yes, yes, that's correct. That's actually coming from the fact that zeta is less than 1. You are actually finding out the roots and you are ensuring that the determinant is less than 0, right?
Yes, ma'am.
Yes, that actually what the solution when you have zeta is between 0 to 1, and from that only we are able to write such type of roots. Okay.
Ma'am, this
Yes, yes, that's the same thing only.
it will work in every question.
Yeah, that would work because that solution is only coming from the fact that zeta is between 0 to 1. Then only we have a roots like this. If you find out the derivation of this root, that is only derived from that concept only.
Okay, ma'am.
Okay, for the same problem, we are dealing with the same transfer function for all these questions. Find out the type of the system, the type of the open loop transfer function. First, tell me what is the open loop transfer function? It is nothing but GS only.
G of CS.
Yes. So H is 1, so it is just PS into CS. And we have already calculated it as Kp by 2s minus 4. Okay. How can we find out the type of system? Type 0, type 1, type 2 or type 3? For that we need to extract the maximum degree of S from the denominator, and here we can see that the highest power that we can extract is just S ki power 0 because we have constant term here. Now can you identify the type? It is nothing but a type 0 system because here the power of S is 0. For a closed loop system, the characteristic polynomial is given as s cube plus k s square plus 2s plus 4. The closed loop system is stable for,
Excuse me, ma'am. The
yes,
previous question I didn't get it.
this
Previous
question,
question.
this one.
Yeah.
Okay, the type we,
Number of poles in the origin will tell about type of the system. Is it so?
yes, so in order to do so, there should be some term where we have s, right? Then only we can have a pole at the origin. But there are no terms where we have multiplicity with s only. There are no terms. You can see from here, right? Other way to check is that the maximum s that we can extract from the denominator. We cannot extract any s from here because we have a constant term here. So s to the power 0 means 1 only. So there are no poles at the origin. You can say like that also. So this is a type 0 system. Now for this system, find the range of k for the closed loop system to be stable. Okay, let's use the Routh-Hurwitz because this is a third order polynomial. We cannot use just the concept of coefficient non-zero and no sign change, because that is the necessary and sufficient condition for till quadratic polynomial only. For n greater than equal to 3, we need to use the Routh table. This will be the Routh table. Now in order to have no sign change, what are the conditions? Okay, so in order to have no sign change here, we need to ensure k is greater than 0. Okay, to have no sign change here, we have to ensure this is greater than 0. From here, the condition is k should be greater than 2. Okay, and there are no sign change here also, so no need to do anything. K should be greater than 2. Okay. Okay, let's solve some other questions. In this question, we are given the first two rows of a Routh table and we are given some options. Identify which option is correct. Are you now able to solve the problems given in the assignments?
B.
Okay, let me write all the options first. This is the Routh table with two entries, two rows. Identify which option is correct. We have a third order equation.
D, ma'am.
B. Okay.
D.
Everyone is getting B.
Yes, yes. D. D.
Are you sure?
D, ma'am.
D, ma'am.
D, plus or minus J.
Yes. Now that's the correct answer. So very simple. If we complete the table, we'll get it as 0, 0 again. Then we have to find out the auxiliary equation using just the above row. We can write 4 is square plus 4 is 0. So S will be plus minus J. From here we have calculated that A and B are the choices. Then we have to find out the third root. For that we complete the table using the derivative of ps. So dp by ds will be 8s. Then we can rewrite the table as 8 and 0, and S0 will be what it will be
4. 4.
4 only. And we can see here there are no sign change. It means that there are no poles on the RHP. So the other pole must be in the LHP. So therefore option D is correct. Okay. We can solve one more question. We are given the forward path transfer function of unity negative feedback system. So G is given as K by S plus 2 and S minus 1. Find K, which will place both poles of closed loop system at the same location. We are given the forward path transfer function, which is nothing but g, and we need to find out k such that both the poles are on the same location. Please try it. What will be the closed loop transfer function?
A square.
K by S square plus S plus K minus 2.
Yes, ma'am.
So it is given as g by 1 plus gh. G we are given this will be nothing but k by s square plus s minus 2 plus k. Is it
So
correct?
answer is 2.25.
Yes. Okay. So for here the characteristic equation is s square plus s minus 2 plus k equals to 0. How can we ensure that both the poles are on the same location for this one?
One minus eta square would be 0.
Yes. So for second order system, we know that we can write the poles as, or you can use the concept of roots of polynomial also, like the way you have solved the previous question, you can use that concept also. For this one, we need to have both the poles on the same location, means that is only possible when
The imaginary part is 0.
okay, if we have some complex pole, then that will lie maybe here or here. Okay, that will not lie on the same location. So we need to get rid of complex poles. And how can we get rid of complex poles? We need to put this complex term to be 0. Okay, and to have poles on the same
Once
location.
again,
Yes.
once again,
Once again, okay. So if the poles are complex, then they will always lie on the symmetric location. They will not lie on the same location. We need to ensure the poles are on the same location, right? In order to have so, if we do something such that this term is 0, then all the poles will be at, both the poles will be at minus zeta omega n. Correct?
Yes, ma'am.
And how can we put this term to be 0? One way is we can put omega n to be 0. Then in that case, this pole will also be 0, and we have repeated poles at the origin, which is not good, because in that case the system will not be Bibo stable. So we cannot choose omega n to be 0. What we can choose? We can choose 1 minus zeta square to be 0. Then this box term will be 0. So the condition is zeta square should be 1. Now what is zeta for our system? Our characteristic polynomial is s square plus s plus k minus 2. So 2 zeta omega n is 1 and omega n square is k minus 2. So from here omega n is under root k minus 2. Therefore zeta is 1 by 2 omega n, and if I square it, it will be 1 by 4 omega n square should be equal to 1, which means 1 by 4 k minus 2 should be equal to 1. So k minus 2 equals to 1 by 4, and k will be, which if you solve you will get 2.25. Is it clear?
Ma'am, we can equate omega n square equal to 0.
If you put omega n equals to 0, then both the poles will be at the origin, and which is not a desirable case. If you have a repeated pole at the origin, then the system will be unstable. Okay. Unstable system we don't want.
If we equate it to 0, we'll get unstable system.
Yes, 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 yes. If we have a repeated pole at the origin, or we have a repeated pole on the imaginary axis, the system will be unstable. It will not be a Bibo stable. One question I am writing for you to try as a homework, you can say. Consider
Ma'am,
polynomial. Yes.
how omega, if we equate omega n to 0, the system will not be unstable.
Will not be, sorry.
No, ma'am, I got it.
If you put omega in 0, it will be what? 0 and 0 only.
Okay, ma'am.
Consider the polynomial s cube plus a2 s square plus a1s plus a naught with all real coefficients it is known that its derivative dp by ds has no real roots. Number of real roots of PS is. You are given a third order polynomial and all the coefficients are real. For its derivative, you know that there are no real roots, and then you have to identify how many real roots are present for the polynomial PS. The question is clear to all?
Answer 1, ma'am.
First you try, we will discuss it in the next session.
Okay, ma'am.
Okay. If you have any doubt, you can ask. So that's all for today. Next week we will meet to solve some more problems. And with this much of content, you will be able to solve the assignment questions of week 5.
Ma'am, I have one doubt now.
Yes.
Ma'am, when there is a case when zero entry occurs in first column, ma'am, we use that positive number e.
Yes.
There we have a case of conjugate roots, ma'am.
If there is a single zero, then no. All the entries of that row should be 0 for that.
Okay, ma'am. All the entries of the row are 0. And then
Yes.
we have conjugate false.
Yes, yes.
And then they will always be in the imaginary axis.
No, for that you have to form the auxiliary equation using the row just above it.
Yes, ma'am. Ma'am,
And the roots of that polynomial will help you to decide whether the roots are purely imaginary or they are complex conjugate but lying on LHP or complex conjugate lying on RHP. But the roots will be symmetric.
okay, ma'am.
Yes.
I have tried to calculate that kind of situation using Scilab, ma'am. There, uh, when I find out the roots with the imaginary part is same as we find with the help of auxiliary equation, but in the real part there is some value. Sometimes it comes
Yes.
positive, sometimes it comes negative, but it is very small, ma'am. 2.22 to the power 10 to the power minus 16. In that case, should we take it to be on the imaginary axis, or we will say that it is on the right half plane, ma'am? To
Epsilon thing you can use only when you have single zero on the column. If you have all the rows 0, all the entries of a row 0, you have to calculate using the auxiliary one.
ma'am, let me give an example to clear this situation, ma'am. If we have the equation s cube plus s square plus 4s plus 4,
SQ plus
s square plus 4s plus 4,
mm-hmm.
here there will be a zero entry row in the third row.
Let me solve it. 1 and 4, 1 and 4. right?
Yes, ma'am.
And this will be 4 minus 4 0. Yes. Mhm.
Yes, ma'am. So here we have to form the auxiliary equation.
Yes, that will be s square plus 4 equals to 0.
Yes, ma'am. This will give
So this
plus
will
minus 2j.
be, yes, directly you can write s will be plus minus 2j. Yes.
Yes, ma'am. But while finding the roots of this polynomial using Scilab, it is a software similar to MATLAB, ma'am.
Okay, Scilab you are using. Okay.
Yes,
Mm-hmm.
yes, ma'am. With these complex roots, in these complex roots, there is a
Mm-hmm.
positive real part, ma'am, but it is very small.
It is very
2.2,
small. Yes, yes, yes.
2.22 into 10 to the power minus 16.
Okay.
This is the real part, ma'am. But it is not zero, so we cannot say that these roots are will be on the imaginary axis. But using the auxiliary equation, the real parts comes out to be zero, ma'am. We should we follow, ma'am. Software results or these results of the auxiliary equation.
Let's try a very simple thing. Okay. Let's put 2j in this equation.
Okay.
What it will be? It will be minus 8j,
8, yes, ma'am, minus 8.
and then um, 4j minus, sorry, only 4 na? Minus 4?
Minus 4, minus 4, ma'am.
Yes, yes, I'm putting 2j, and then it will be plus 8j and plus 4. What you are getting?
0.
Then what is the answer?
Yes, it should be.